Cool. Okay, so let's start with what is an image. So an image for us is just a small visual representation, but what do you think the image is for a computer? Anyone who has an idea?
Just a bunch of ones and zeros.
Not just bunch of ones and zeros, but it's like bunch of different numbers. Again, it depends on whether you're doing RGB or like just black and white channels, but it's usually a bunch of different type of numbers. Uh, so yeah, so just a small matrix of m into n with like bunch of numbers inside it. So again, it's going to be a redundant question, but which one do you think is an image in all of these cases? Like, okay, how many images do you think there is over here?
One.
5?
One image reconstructed. So
Uh, might be. This is just a trick question. It's just one big image, I'm saying. Small joke, but yeah, just a small joke. So again, these actually these four are again images over here in this slide. So this is just the like how it's represented in matrix form, the numbers. The other one is just showing the gradient of it. The other one is like what you said, reconstructed, and the other one is the original image. So we go over here. So the image that I showed you in the last one is just basically a black and white type of thing with just one channel is your input in the CNN. But usually if you're dealing with like RGB values, which is like red, blue, and green, you usually get three channels in that case. And you will have to feed basically three channels to your CNN architecture. So over here, if you see, again, you just give it in terms of RGB as your channels and you process it inside your CNN network. So go to the next slide. Again, we just covered last in the boot camp as well, like just like a very rough idea of CNN, but I think in the lectures we did it comprehensively. So CNN is just a specialized neural network which employs convolutional and pooling layers to extract features and hierarchical patterns automatically from the input. It's basically used for any sort of image task per se, because you don't lose your spatial information with regards to that. Again, when we go to the next slide, you'll see MLP versus CNN. I talked about this in the bootcamp last time, but does anyone know why we don't use MLP for image application tasks? Yeah.
Like the location and variance.
Correct. That's one point. That's good.
computational intensity.
Yes. And there's one more important thing as well. Anyone else from Zoom? No, that
Too
again.
many parameters.
Yeah, so that is basically computational complexity, but there is one more important thing that we are missing, which is the main reason why we use CNNs. That is basically losing out your spatial information. So if you're putting it inside an MLP, it's tough to reconstruct it back to a 2D plane. But in CNN, you're just basically doing a feature map to a feature map extraction. So you don't lose any spatial information in that regards. But again, like I said, computational complexity is again one of the big factors into the play. And also the other point that was mentioned was, I think, translational invariance. That's also one of the more important factors why we use CNNs compared to MLP. But again, one of the another bigger factor is to not lose your spatial information. So let's talk about the building blocks of CNN over here. There are two very important building blocks in a CNN. That's basically your convolutional layer and pooling layer. I think we covered this in depth even in the lectures, but in this lecture, in this recitation, we'll just cover up how the maths is involved inside it. And there are other things that can also be found in CNN, but they're also found in MLP. Those are like activation layers, normalization layers, and your batch norm. So hyperparameters. This is something that's going to be like very important, especially for your homework 2B2s. And in CNN in general as well. The thing is kernel size, stride, how much stride you want to do for each image, the number of filters in it, and padding. For a pooling layer, it's just basically a pooling type, size, and stride. That's totally fine. And number of layers is again another hyperparameter which you always play around with. So I would say you will have to do basically some of this hyperparameter tuning in your homework too, P2s. But in general, when you're using CNNs as well, you need to like think deeply on like how to change these parameters and construct an ideal network for your model. So yeah, convolutional layer, again, it's one of the core components of CNN. They basically apply your convolutional operations using something called filters slash kernels to your input data. And these filters slide across the input to detect patterns, edges, and features. But the sliding depends again on what is your stride and basically on your kernel size and everything so on. So you go here. Yeah. So does anyone know what is the ideal kernel size, what people use all the time? So the answer is there is no ideal size. It's always an ablation study in the end of the day. Uh, but if you go look into like the past papers, especially of let's say ResNets, ConvNext, or any of the CNN architectures that they provide, they usually use either a kernel size of 3, 5, or 7. But another question I have is why can't we use, let's say, why are we using always a square kernel size? Why can't we use a rectangular or let's say a different type of dimension? Like instead of 3 into 3, why can't we do a 3 into 5 kernel size? Any idea? Technically, you can, but why don't people do it?
Is it because the source image or training image is square?
Again, I can just put a normal rectangular image into my data and just throw it in, right?
Maybe some type of symmetry preference,
There is a symmetry preference, but why?
compensation.
Yeah. At the end of the day, it goes to computation, which is true. Because if you make it like rectangular or like, let's say, some other type of dimension, it basically increases your computational complexity because like now there is more things the network needs to do to basically keep it stable. If it doesn't do that, then again, your answers will go to NAND and all that. You'll basically blow up your network in that case due to vanishing gradient or exploding gradients. So because of that, most of the time the networks, what they do is even if your image is rectangular or in like weird size, uh, they essentially just crop it to a square matrix and then do their calculations on it. So that's a factor which you have to take into account, especially even for your projects, because many of the time I've noticed that for your projects, if you're making your own data set, you will be coming across like different sizes of images. You have to basically crop it into a square or any of that shape and then put in your network. Don't try to play with like different type of kernel sizes like 3 into 5 or like 5 into 8. Just like try sticking it with the norm. I'm saying that's it. So stride. We covered this in the lecture. Does anyone want to say anything about it? Like why do we stride or anything like that?
Upsampling and downsampling.
Yeah, upsampling, downsampling, but why does that help? Yep.
Isn't it equivalent to, like, if you have a stride two, it's equivalent to doing the convolution with stride one and then downsampling the two, so you're just like reducing the amount of computation you have to do.
Exactly. So it's basically to reduce the number of complexity. I mean, like computation you need to do in your model. So that's why like people do your striding. But again, that's ablation study which people do, and there is a formula at the end which people apply, which I'll show you. Might help. Let's see. Padding. Did we cover this in the lecture? I think we did. Do you guys know why do we do padding? First year? Like, where do you think padding will be important? Yep.
Want to preserve your spatial dimensions.
Can you repeat it? Sorry.
If you want to preserve your spatial dimensions.
Exactly, correct. So let's say if you're using a kernel size of let's say 3 into 3 and your image is size of like 5 into 5, you might want to like preserve the last two bits of your image. So for that, you would probably like try applying a padding so that you don't like lose out the information in there. So that's why people like use padding with regards to it. Uh, Convolution, we are just going to like go deep into like the maths behind it so that we can understand like how it happens. I mean, it's pretty simple. So let's assume we have input image of 4 into 4. You have a kernel size of 2 into 2. What people do is basically you just take the weights of your kernel, apply it to the first part of your image, and then just add up all of them together. It's just going to be like A11 times W11 plus A12 times W12 plus so on, so on, so on. And then like at the end, you just apply the bias on it. And that's basically a first Z value. You do that like as many times as needed, but we'll see. So does anyone know the formula to get the output channel? Like how many layers? I mean, like what is the dimension of output channel? Does anyone know the formula for that? Yeah. Okay. Correct. So if we go over here, it's not -1, it's +1, but yeah, everything else is correct. It's just in channels minus kernel size time plus 2 times padding divided by your stride plus 1. That's how you calculate your output width. So normally you would need to do this for every convolutional layer to basically like not get any dimensional issues, and especially to figure out what's your final FC layers like output going to be. I mean, to your input going to be for your FC layer. You would basically need to do this calculation for like all your convolutional layers and figure it out, but that's okay. So again, two like P indicates padding, S indicates stride. It's fine. Convolutional neural network. So basically, a convolutional neural network just consists of convolutional layers which have kernels inside them, followed by an activation function, followed by a batch norm. Uh, so I'll just show you like over here how a striding is performed with, let's say, for the same example which we did over there. So basically, for stride 2, now you basically skip 2 times. So before we went from like A11 to like A12 as your starting point. But in this case, it would be like you skipping one row and then going to the next row. I mean, next column, my bad. So it goes from A11 as you're starting to like A13. So if you see, that's how you do it. And then you just go like 2 steps below for your uh, down column as well. So if you look at that, it goes like this, and that's it. Padding, again, it depends on like how much like padding you want to do. People usually like, you have to like do a calculation for it at the end to ensure that you don't lose your spatial information inside your image. Again, that thing, the calculation is done based on this formula, which we have it over here. And like you can just assume whatever the like kernel size you have, whatever input channel you have, you can like put whatever stride you want, and then based on that you can see if you want padding or not to lose your spatial information. So we like I said, padding basically just increases your output size to preserve your input size, and it just allows to get your more kernel interactions. But uh, yeah, so in this case, padding is equal to 1, and they just put padding all around it. So from a 4 into 4 image, it just basically became a 6 into 6 kind of image. So why can't we like do padding only in one side or like in one area? Why do we always make it symmetric? Any question? Any idea?
Symmetry.
Symmetry, but why? Anyone? Yeah,
If you only did it on one side, you want the values of like one side more than the others. So
correct.
I think it would kind of go off the features.
Correct. Exactly. So people have actually tested this out, and like many people came to the conclusion that generally, if you try doing padding in like one side or like only in one part of it, the model doesn't perform well in regards to that. People again say it's due to like some like the uh, network not able to like learn properly due to like some uh, computational thing inside it. But yeah, it's generally recommended to do symmetry rather than like just padding it on one side and hoping that the spatial information is not lost in that. Yeah.
So how do you handle like, images with obfuscations? So like, occluded images.
Occluded images, like, do you mean like if there is some occlusion of
Yeah,
like,
like some partial, but is the image, so like in that face section.
okay,
I noticed in some of the pictures, like part of the face is.
blacked out, okay.
Yeah, black.
So basically, a CNN job is to basically learn the features of the part of it. So if basically it's if your image is occluded, they will only learn the features of the non-occluded part, depending on like how you use up your model. But that's the gist of it. Like if the image is occluded, the other half is basically not going to be viable for your like network. So they'll only learn basically what is present inside it. So even if it's occluded, if you're doing like padding is just like putting in zeros to your image channel. So you hope that your model doesn't like learn in that. Again, if you put a higher number of padding, let's say 20, 30, and just slap it inside your network, it will probably just learn the padded values and then you just get a bunch of bad results in that case. So yeah, with padding, when you do your kernel operation, it takes into account of like the zeros and like gets you up, like you basically have to like do your calculations with the padding part of it. Then yeah, so multi-channel CNNs, that's what basically many of you guys will be using, because for homework 2P2 you are using like RGB images. So we have like input channels of 3 in that case, which you put into your CNN layers, and I mean like your CNN architecture, and then you get out channels based on like how much out channels you put for your network. So I think many guys had confusion in this in the class as well. But for each convolutional layer, you have only one kernel, and that one kernel basically gives you one output channel. It's not like you have like 10 number of input channels and you're telling like you want to get like 64 as your output. That doesn't mean like you'll have 64 kernels for like each convolution happening. No, it's like you basically have for one like for one out channel, you always have only one kernel. That's just one small heads up, because I think like in the last week, I mean the last class, people were confused and as to like how many kernel sizes there for like per output channel. It's just like one kernel for one out channel. That's it. Yeah.
Is it one kernel for one out channel, one in channel? I think you started with one in channel, then you said one out channel.
It's for one out channel, one kernel essentially. So one filter with 3 inputs. Yeah. So again, it's just a normal calculation that happened, but this time you're using with 3 channels. So the calculations is basically you taking the mean across it, and that's like pretty much your calculations for it. Pooling layer, yeah. So usually there are like 2 type of pooling that is applied over here, either mean pooling or max pooling. For max pooling, you basically take the maximum values in your kernel size, whatever you put it as your max pooling value in. And mean pooling is just taking the mean value of your kernels. So if you look at the calculations, uh, over here, I'm just giving an example of stride is equal to 2. So for max pooling, you just take the max value of 4, 8, 16, and 10. That is going to be 16. Then after stride 2, you basically go to 3, 9, 0, 7. Your max value is 9, so you take a 9. Similarly, you take 67 from the below one and you take the 13 one on the next. Mean pooling, you just calculate the mean. So it's going to be 4 plus 8 plus 16 plus 10 divided by 4. And you get 9.5 in that. For the other one, you get 4.75, then 25.75 and 7.75 respectively. Back propagation, I'll let my other TA do it. Mia, if you want, you can share your screen.
Yep. Can you discontinue yours first?
Oh, okay, cool.
Can you discontinue yours so I can share mine?
Oh, sure. My bad.
Thanks. Okay, can everyone hear me?
Yeah, we can.
Okay. All right, so we have backprops for CNNs next. Before that, let's review a little about backpropagation with respect to the chain rule. As an example, let me just start. Okay. So here as an example, we have a function that takes the values x and y and outputs z. And we get the gradient of the loss from the previous layer as dl dz. In order for the loss to be propagated to the other gates, we need to find dl and dx and dl dx and dl dy. So using the chain rule of differentiation, we can find dl dx as the gradient of the loss from the previous layer, dl dz, times dz dx, and dl dy as, again, dl dz times dz dx. So let's think about the function as a convolution, where the convolution is between the input matrix X and a filter F, giving the output of the convolution O. Here, the gradient of the loss from the previous layer is denoted as dl do, and we'd like to solve for dl df and dl dx with the understanding that dl df will be used to update the filter F using learning rate A, and dl dx will become the loss gradient for the previous layer, since dx is the output of the previous layer. Or sorry, since x is the output of the previous layer. Okay, recalling our example of differentiation with function f, with the inputs x and y outputting z, we can similarly use the chain rule of differentiation to find dl df and dl dx, where dl df is the gradient of the loss from the previous layer, dl do, times do df, and dl dx is again dl do times do dx.
Recording in progress.
Sorry.
Okay, so before we move on, I just want to give an analogy that will be useful as an example later. It's just as a thought, we can imagine the filter F being like eyeglasses, the input X being your vision, just using your natural eyesight, and output O as your resulting vision with glasses. We'll get back to that. So going back to the convolution with filter F and input X, we have an example with the operation for this calculation. And here is an animation of the operation calculation where the filter is 2 by 2, the input is 3 by 3, and it's obviously a stride 1, and it results in the 2 by 2 output matrix. So now thinking about the loss gradient, LD or DLDO, what operation do you think we may use in the backward pass? We use the convolution in the forward pass, and separately, we'll need to solve for DLDF and DLDX using convolutions. So let's start with solving for DLDF. We know that using the chain rule, DLDF is equal to DODF times DLDO. Since O and F are matrices, DODF will be a partial derivative of a matrix O with respect to a matrix F, as shown in this formula, using the chain rule. And given that DLDF is represented as the output of a convolution, can anyone guess what matrix goes in the empty space? Okay, here's a hint where we differentiated the first element of O with respect to the elements of F. So the matrix is simply the input X. Going back to the eyesight analogy, this part of the CNN backprop would be like getting better glasses that suit your vision better. So, okay, so that was the filter for DF dx. Now, what about solving for DL dx? We know that using the chain rule, DL dx is equal to DO dx times DL do. And since O and X are matrices, DO dx will also be a partial derivative of a matrix O with respect to a matrix X, as shown in this formula, again, using the chain rule. So given that DL dx is represented as the output of a convolution, can you guess what matrix goes in this empty space? Here's a hint, where we differentiated the first element of O with respect to the elements of X. So it is F, the filter F, but there are two things to think about before we make the convolution. With filter F, before we make a convolution with the filter F and the loss gradient from the previous layer. So back to the eyeglass analogy and also considering the spatial dimension of convolving F with DLDO. This time we're going to look at input X, which we said represents our vision. If we're only testing our natural eyesight, input X, and the forward pass gave us glasses for nearsightedness, so these are nearsighted glasses, that would be filter F. If you can't remove your glasses, if you can't remove the first filter, like you can't take off your nearsighted glasses, and you want to test your natural eyesight or your feature detection, would it make sense to put on another pair of nearsighted glasses and convolve with the same filter? No, it doesn't make sense. So what you need to do is put far-sighted glasses on in addition to your nearsighted glasses, which would, it's in effect flipping the composition, and this would allow you to test your natural eyesight. So you would need to flip the filter once horizontally and once vertically. It's the same as rotating at 180. And so here's the new filter for convolution. You can also think of this as having a base during the forward pass and then needing an acid to neutralize during back propagation. So what about spatial dimension? To get an output that's the same size as the original input X, you'll need to pad the matrix DLDO. So this is what I'm going to see. Sorry. So I'm going to visualize padding, and you'll need to pad the output map with k-1 rows and columns on every side. And you can see the animation of the convolution with the flipped filter and padded output map here. So that was the solution to finding DLDX. And here we have both solutions. The exclamation point is just there to point out that the filter F is backwards, or on the convolution for DLDX, it's flipped. And we can also see it like this, in the output map DLDO. So now what about when we have strides that are greater than 1? The solution's easy. For this, we just dilate the output matrix by the stride -1, and as we see here with the zeros. And then returning back to the convolutions to solve for DLDF and DLDX, we can just replace the original output map with the dilated version. And that's how you do backprop for CNNs. And now Dennis is going to take over for Kahoot.
All right, let me share my screen.
Okay.
So we couldn't set up the Kahoot because it requires they can only allow 10 participants. So we decided to have the questions in form of a PDF. But so here I'll give you a couple of minutes to work through this question, and then after that we can work through it together. So the first question is about a convolution with 1D CNN. So here the question reads: a convolution layer over 1D CNN, that's a time delay neural network, operates on the following input. So the Y is given here, with the following two convolution filters, which are also given. So the filters operate on input Y to compute the output Z. The convolution uses a stride of 1. Now the question is, what is the second value of the second channel of Z? That is Z22, where the first index represents the channel and the indexing is 1 base. So instead of having 0 best indexing, we have 1 best indexing. Could you please work it out in, I think, like 2 minutes? Then I can walk through the solution. So once you're done, you can say the answer out.
Anyone put an answer? Is it 0?
Okay, you said 0, okay.
Yeah,
What of,
Dennis, can you give the answer?
yeah, what of the other guys? Has everyone finished working it out? I can.
Yeah.
All right. Yeah, so could a person who like said out the answer try to explain how they came up with it?
How did you came up with it?
I
Yeah,
usually use W2 and then I move one straight over. This is one index and then I do the multiplication. Then I got just a bunch of zeros.
Correct. So he basically used W2. He tried it one by one bit and just did the convolution and got the answer as 0.
yes. So that's right. So what we do is we know that the value that's required is from the second channel of Z, and that can only be produced by the filter W2. So what we'll do in this case is get filter W2 and place it on top of this input so for example, in the first step, we shall have 0 overlapping with 1 and 1 overlapping with 1, then the two zeros covering each other. So we shall multiply those elements. We shall multiply element ways and sum. So in this first step, we shall get 1. Then when we move to the next stage, we shall have the filter W2 overlapping with the input. And in this case, we shall have the 0 overlapping with the 1, the 1 overlapping with the 0, the 1 with the 0 at the bottom, and the 0 at the bottom with the 1 here in the input. And in this case, we shall get 0. When we multiply and add, we get 0 as our output, which is the required answer in this question.
Yeah.
Does everyone understand how we came up with the solution?
So does anyone have doubts in that regards on how he got the solution? So basically what happened was he used W2, he started by one bit and then he did a convolution in that area and he summed it and he got it to a 0. Okay. Like these type of questions may or may not come in the quiz of this week. So just a heads up. Cool. Next.
So now we shall look at the second question, which is a bit more complicated, but will enable you to work out what happens when we have multiple channels and 2D CNNs. So the question here reads, a convolution layer of a 2D CNN operates on the following input. The input is 2 channels of 4 by 4 represented by the two 4 by 4 matrices, where the left matrix represents the first channel and the right matrix represents the second channel with the following convolution filters. So here we provide the two filters, W1 and W2. Then it goes ahead to say that the filters operate on input Y to compute the output Z. The convolution uses a stride of 2. What is the value at position 2, of the first channel of Z, i.e. Z122, where the first index represents the channel? The indexing is 1 best, so indices start at 1. Could you take a couple of minutes to work out the solution?
actually get to it, which one is
So has anyone managed to work out the answer here?
So anyone got the answer?
I see one in the chat, but I'm wondering whether anyone physically present has the answer.
I calculated 4.
Okay. Could you like explain how you came up with it? That's okay.
So I used the first filter because we want the first channel of the output and we want position 2, 2. So I took the lower right half 1001 for the first one and it gives 1 plus 1. And for the second channel, the lower right half, so it gives 1 plus 1 again. So I add both the channels, it gives 2 plus 2, 4.
Yeah, I think yeah, that's right. So if I could go over the entire operation, and the way it works is we shall get the filter W1 and overlap it, place it on top of this input. So we shall have these numbers, one over covering 1, 2 covering the 0, the 2 over the 0, and again 1 over the 1. Then same thing happens in the second filter. So this first matrix is placed on top of this matrix here in the input, and the second one is also placed on top of this other one. Then what we do is we carry out an element-wise multiplication and sum the numbers within that window. So when we do that, we get a single value for this region and this region. So get a single number here and another one here. We sum the two to get the output of this filter, the output of this filter. Then we repeat that throughout the input, taking a straight of 2. So the next position for this filter will not be this region starting from 0, 1, 1, 0. We shall instead place it over these last two numbers, these last two columns. So we shall have the one overlapping with the one, the two overlapping with 0, then 2 with 0 again, and 1 over 1. We do the same thing on the right with the right hand matrix, and repeat the operation of an element-wise multiplication and addition. And after repeating that process, we get to our position of interest, which is the bottom right corner, where we shall have the first filter W1 overlapping with this input. We will do the multiplication and add up to get our solution. And that's how he came up with the answer of 4. So is that clear to everyone? All right, so if that's clear, I think we can move forward to the third question. So this one is again 1D CNN. So here, convolution layer of 1D CNN operates on the following input, where Y is given as that, with the following convolution filter. So this time we have 3 filters. So the filters operate on input Y to compute the output Z. The convolution uses a straight of 2. No zero padding is employed in the forward pass. What is the 2 elements? That's the second element of the output Z. So here I could start by asking, what do you think the shape of the output would be? Like, how many channels will it have in this case, and what will be its area? Does anyone have an answer? Yes, so someone says 3 channels and it's 2 by 2. So using the formula that was provided by Hanan as he was explaining convolutions, we can work out the output size by using the formula that output size is equal to input size minus the kernel width plus 2 times padding divided by, so we use integer division over the straight and add 1. That's how we are able to come out with the output size. Then we know that the number of channels in the output is equal to the number of filters that we have that we're using in the convolution. So in this case, we shall have 3 channels in our output. So in this case, could you go ahead to compute the result of this operation?
Which channel do we have to calculate? There'll be 3 channels in the output.
Okay, yes. So here it says, what is the element in position 2, of the output Z? So when you get your output, you'll arrange it in terms of so each channel will be represented by a row in the output. So we want the element that will be in this position. Since we have 3 channels, then in that case we want the element that will be in this position. That's 2.
So basically, he's telling about the second channel output, the second channel's second output.
So you said it was like 3 channels of 2 by 2, but how would it not just be 3 channels of a 2-dimensional? It's a 3 by 2, right? Because if you,
Yeah, it is a two.
okay, I thought you said 3 channels of a 2 by 2.
No, he meant 3 by 2, so it's like, basically, it's like every channel you just stack it on top of it and it becomes a 3. Yeah, it's basically second channel, second output. So
Is there
Does anyone have the answer?
YouTube? Zero.
0?
Yes, I think it's 0. So I think this is just similar to the first question that we had. I don't think there's much difference. So you can use the procedure that we used to calculate the answer for the first question to obtain the answer here. So I think then we can move forward to this to number 4, which should be straightforward, I think. So here the question is, while back propagating through a mean pooling layer, the divergence derivative at the output of a mean pool filter is. So here we're asking, for example, you have the output, which will be like, if your output, for example, if our input is Y, we're using filters F, and we obtain output Z or O. So we have the derivative with respect to the output, which is, for example, dl dz. So, but then we want to obtain the derivative with respect to the filter. How do we distribute the output over the derivative from the output over the filter that we use to calculate the mean pool? So the first option is it's equally distributed across the pool area. Then the second one says it's weighted by the value of the pool. So for example, if we have our pooling, if the elements within the input were say 1, 2, 3, and 4, and we're using a 2 by 2 region, the weighted by value means that if the value in the input was 2, it will get more of the output compared to a value of 1. So that's what this option means. Then, so here the third option is pass to only the maximum value in the pool area. So that's like the region that we are considering for mean pooling. And the third one is the last one is 0. So what do you think is the answer in this case? And I think if you've attempted homework 2 part 1, this I think a similar question must have come across a similar question. So one person says it's B. Do you agree?
What does pool area mean? What do you mean by that? Just like the amount of elements, like the dimensions of the pooling portion?
So that's it means that like the area over which you're applying the mean pooling. So for example, if you have an input of 3 by 3 and you're trying to do mean pooling using a 2 by 2 region. So the 2 by 2 region is what I'm referring to in this case.
Does anyone have a guess for this?
Yeah, what's your solution?
I think it's equally distributed, but it has to account for like the pool size. I still don't know if I fully understand what you mean by the pool area.
So, okay, let's take this as an example. So let's say you're carrying out mean pooling over this region. So this is what I'm referring to as the pool area, the mean pooling area. Do you get it now?
Kind of, it seems like my misunderstanding is that A and B seem like they're like identical if you talk about them like that. Like what's the
Like, so if you were to draw the influence diagram from each of those like four. Do it right, like taking the mean over them, it would distribute evenly. That each of them contribute just their contributions. to the
Yeah.
mean, Right. Does that, not sure.
But that's what A is saying, right? It's like each of
That's
their.
what,
each of their
yeah, that's what
contributions.
A is. Yeah.
Okay, so one person says the answer is B. Do you agree? Who has a different answer?
You can go for it, you might have it.
I mean, I think it's A.
We've got an A in the room, Dennis.
All right, all right. Yeah, so I think if you've gone through the homework, you should know that when you're carrying out when you're back propagating through the mean pooling layer, you use 1 divided by, so if it is a 2 by 2 region, you use 1 over k squared, where k is your kernel size. Then you multiply that by the derivative from the output, and each of the elements within that region gets that as its gradient. So we shall move on to the next question. So this one says, when back propagating through a max pooling layer, the divergence derivative at the output of a of a max pool filter is. So in this case, we are using max pooling.
What was the answer to the last one?
So the answer was A,
Okay.
which is equally distributed across the pool area. So yeah, number 5 goes while back propagating through a max pooling layer, the divergence derivative at the output of a max pool filter is. So option A is 0. Option B says assigned to the input location of the maximum value in the pool region. Then C goes equally distributed across the pool area. Then D is weighted by value of the pool area. So in this case, what's the likely answer?
Yeah, there's, I heard B in the room.
Yeah. So like you've covered, this will be B. It will be assigned only to so it's only the biggest number within that region that contributes to the output. And when we are back propagating, we assign the gradients only to that to that number. So then now I think we can move on to question 6, which covers depthwise convolutions. So here we have the input to a 2D convolution layer is size 28 by 28. So we have our input, which is 28 by 28, with 32 input channels. We wish to perform a convolution using channels of size 5 by 5 on it to obtain 32 output channels. No bias is employed. What is the difference in the number of parameters to be learned between a conventional convolution layer and a deploy separable convolution layer? So A goes the regular convnet and the deploy separable network both need 800 parameters, but they are distributed differently across filters and layers. Option B is the regular convnet needs 1024 parameters, while the deploy separable convolution needs 800 parameters. Then C is the regular convnet and the deploy separable convolution both need 1824 parameters. And D says the regular convnet requires 25,600 parameters, while deploy separable convolution needs 1824 parameters. So which one do you think is the answer?
What's the difference between a conventional convolution and depthwise convolution?
Yeah. So if we are to refer, so I'm going to refer to the convolution that Hanan was showing you in the first part of the recitation, where he showed where you have each channel of the filter interacting with the channel in the input. And so if we want an output of 32 channels, we shall have 32 such filters. So we know that each filter has to have the same number of channels as the input. So in this case, if you have an image with 3 channels, the filter that you're going to apply to this image should also have 3 channels. And if you want an output of 32 channels, then you must have 32 filters, each with 3 channels. Then we can then consider the kernel size. But then in depthwise convolution, what we do is you're going to apply one filter and then so we're going to apply one filter which has number of channels equal to the number of channels in the input. And then instead of repeating that process using different filters, we shall apply a function that computes the output for each of the 32 outputs. So instead of repeating the process, we use I think, has this been covered? Sorry if I'm going ahead. Has this been covered in class?
No.
Okay, I think we can leave it out because I think professor will give like a better explanation for this. Yeah, but that's the way it works. Instead of using 32 filters, if we needed a 32 channel output, it would use only one filter and apply a function to calculate the 32 outputs that we're interested in. But I think this will be covered better in class, and you can then come back to answer this question. Yeah, so we can move.
One question on that. In question 2 that you showed, right? Should we consider normal regular convolution or depthwise convolution?
No, the ordinary.
Is that making sense? I mean, from my understanding, what you're saying is depthwise convolution will have the same filter for all the channels. Is that correct?
Yeah.
So,
but then
in that case,
okay. So in number 2, we had 2 filters. So in that case, we're considering the vanilla CNN, where you're just applying different filters to obtain different channels of the output.
okay. So if there was just a one filter for both the channels, then it would have been a depthwise convolution. Is that correct?
Yes. So no,
Okay.
if I could show you. So here we have we have 2 filters. So if we were to use a depthwise convolution, in that case, would have only one filter, then apply a function to the output of that filter to obtain the output that we're interested in.
Oh, okay. Got it.
So moving on to number 7, which covers some of the stuff me had looked at. So here the question says, how do we obtain the derivative with respect to the input given the derivative with respect to to the output. So here we're looking at a convolution. So you have your for instance, if you have your input image, you're going to apply a filter to that image and obtain the output. Now we are given the derivative with respect to the output, and we're required, the question is, how do we compute the derivative with respect to the input? So option A goes, convolve the derivative with respect to the output with the filter after flipping it left to right. So that's like a horizontal flip. Then B says pad the derivative with respect to the output with zeros and convolve it with the filter. Then C says pad the derivative with respect to the output with zeros and convolve it with the filter after flipping it left to right and top to bottom. Then D says pad the derivative with respect to the filter with zeros and convolve it with the filter after flipping it left to right. So from what was covered during this recitation, you can give us the answer. Yeah. Yeah, so here I think there's someone given the answer in the chat, and he says it's C, which is the right answer. I think if you look at the material in this recitation, you'd be able to obtain the answer. Then we can move on. This is the last question. So it says, how do we obtain the derivative with respect to the filters given the derivative with respect to the output of the convolution? So in the previous question, we're looking at the derivative with respect to the input. Now we want to obtain the derivative with respect to the filters used for this convolution. So here, A says pad the derivative with respect to the output with zeros and convolve it with a filter after flipping it left to right and top to bottom. Then B says convolve the input with the derivative from the next layer. Then C says pad the derivative from the next layer with zeros and convolve it with the input. Then D says flip the output left to right, top to bottom, and convolve it with the input. So yeah, what's the solution here? Yeah. So is there someone in the class who can tell us the answer? Or in the chat?
I guess it's just C, because according to just what I learned from the previous speaker about the rest the derivatives.
Okay. Yeah, what do the others think?
I think it's B. I don't think you have to pad the filter. The inverse. Like.
You don't need to pad when you're updating the filter.
Yeah. So, yes, that's the answer. So that's all for the quiz, the mini quiz that we had here. I've also provided if you would like to look at the solution, I provided the solutions at the bottom of the PDF, and I will share this after this recitation. Thank you.
If you think about this, if say you I don't know, like 7, just go one of the 7 times.
Thanks, Dennis.
And you that's what you're doing there. You think about that's probably gonna give them 5.
All right, guys, any questions before we wrap up? I think Dennis, Mia, that's all you guys had planned, correct?
Yeah.
Yes.
you.
Thank you.
Okay, perfect. Your timing's amazing. The pizza just came in, so thank you so much.
See ya.